let us continue with the demonstration of how you can actually do a thermal actuator. The thermal actuator, as you can see over here in the screen, you have one polysilicon which is having the length in order of micrometers, and you can see over here it's having a thickness of around only 2 micrometers, and the the leg that you can see over here, the leg which is going to get heated up, which is also known as the hot arm, is having the width of around 3 micrometers. There would be 3 anchors with which it's going to get attached to, and there are 3 dimples with which it's going to roll on with. The main application of this thermal actuator is to give a motion. For example, you want to give an input of a voltage and you want to see if this particular system moves with a particular value in order of micrometers. This system being in order of having the length in order of, I think it would be order of hundreds of micrometers, would move in order of within tens of micrometers. So let us see how to actually model this kind of a multi-physics coupling, because over here there are 3 physics that are going to get into the picture. The first physics is the input current that we give. Because of the input current or the voltage that we give, there would be a certain rise in temperature because of Joule losses, and because of the Joule losses there is going to be some kind of thermal expansion, because each material has its own thermal expansion coefficient. This is what we are going to couple. We are going to couple the electrical physics with the thermal physics and the structural physics, which leads to deformation. Our end goal is to see if we change the voltage, how much is the maximum displacement does the thermal actuator gives. So let us go and try to understand the physics step by step. The first physics is the electrical physics. So in the circuit that you can see over here, what you see over here, we actually are going to apply a particular voltage at one of the edge over here, that is one of the anchors over here, and we are going to pull the ground somewhere over here. The voltage with which we give could be actually coming up through a very big circuit. Let us now go to COMSOL. So this is the first screen that you will see once you open COMSOL. If you are a little bit experienced, you can go ahead and make a blank model. So you don't need to add any physics. Just a one click will lead you to a complete new model, a blank completely model. The model wizard is a step by step process to make or initialize your model. So let us click on model wizard, and it's asking us for the space dimension, whether you want to make a three-dimensional object, 2D axisymmetry, 1D axisymmetry, 1D or 0D. So let us go ahead with 3D. Now it's asking about which physics that you want to add. As of now, we know that there are going to be 3 physics that are going to play a role. The first physics is the electrical physics, second is the thermal physics, and the third is the structural mechanics physics, which is going to lead for deformation. The first thing that we are going to add is only the electrical physics. We will see how the potential is varying throughout your domain, how is the current getting accumulated at some part of your domain, which is actually leading to the thermal losses, and that losses is eventually going to go to the thermal step. So our first step is to do only the electrical physics. So let us go into the AC/DC module, right. So this is the AC/DC part, and in this AC/DC part there are a lot of different interfaces, electrical current interface, magnetic field interface, rotating machinery magnetic interface where you can model motors. As of now, we will go ahead with only the electrical currents. Okay. This specific interface is to model currents through conductors. If you are talking about capacitors, then you need electrostatics. So let us go with electric currents and add. So I can go to the next part as the study. Here there are many different kinds of studies we can perform. We can do frequency domain study, which allows us to do harmonic input. We have stationary study, where we can give a steady state analysis, that is we give only a particular voltage. Then we have time dependent study, which helps you to give you transient analysis of your complete system. So all these three different kinds of study can be performed. Along with this, we have small signal analysis, wherein we give a particular DC bias along with the AC component. So let us go with a stationary analysis and click on done. So the approach that you can follow in COMSOL is the top to bottom approach. That is, you first create the geometry, add the material, add the physics, then perform the meshing, then you do which kind of analysis you want to perform, and finally the results. So this is a top to bottom approach that usually is preferred in COMSOL. One more approach which is preferred is in the ribbon pane that you can see in the top. Here you can see that the same thing that you have already seen in the model builder. You have to first create the geometry, add the materials, apply the physics, perform the meshing, analyze the which kind of analysis you want to perform, then finally the results, that is to analyze your results. We also have one more block as developer, that is if you want to write your own code along with the code that is being solved by COMSOL. So the first thing is to make the geometry. However, to save the time, I am going to import the geometry. There are two ways to import the geometry. One is to import through some other tool, any other CAD tool, and if you want to insert a sequence is like a step by step process to make the geometry. If you want to insert that sequence from a pre-built COMSOL file, you can use a insert sequence. So let me choose insert sequence, and I choose the model that I have already created, and I click on zoom extents. So this is the geometry that it's already available in the library file. So if you want to go through this example model, which is also known as thermal actuator, you can go to file, application library, and just search for thermal actuator, and you will see the thermal actuator model file available over here. So I have added the geometric sequence, as you can see over here. The next thing is to add the materials. So let me just add the material by right clicking the material, add material from library. I can go ahead in the built in, I can have the polysilicon material property. Now we can see that over here the material property, it is including electric conductivity, which is being defined as sigma as a function of T. This T is the temperature. What it means is that the sigma is not constant, it is a function of temperature. If you want to see what is the relationship, you can open this polysilicon and then go into the analytical function which is define the conductivity, and if you can plot, you can see how the conductivity is decreasing with the increase in the temperature. The next thing is to give the physics boundary condition. As you can see over here, we give apply a particular voltage at this anchor and ground at this particular boundary. There are different ways of applying the boundary. For example, you can use electric potential. Another way is to use terminal if you want to evaluate the resistance offered by your system. For example, I want to know the resistance offered by a system. So, I will go ahead with the terminal and I apply that particular boundary over here, and I give the terminal type as voltage, and I choose the voltage as V naught. So, right now you can see that it is showing unknown variable, because we have given a variable name, but you have not defined in the parameters. So, let me go to the parameters. This all parameters have already been assigned, or it has already come up, because we have imported a sequence of geometry steps. So, these all parameters are defining the geometry steps. Let me define now V naught, which is around 5 volts, that is the operating voltage. So, now the error has ceased to existence. So, there is no error. We have given a voltage over here. So, let me also give a ground boundary condition on this particular part over here. Okay. Let me go to the mesh and click on build all mesh. So, this mesh that you can see over here is fine enough. If you want to improve the mesh, you can directly go to fine or finer. With me, I think fine should be good enough. No, now you can see that your actually the dimple was cylindrical, but over here it is not even a cylinder, right. So, this mesh might not be sufficient enough, because your geometry might be having the cylinder, but the physics is going to be solved only how the mesh is being so it's actually is going to solve the way the mesh behaves or looks like. So, we need to go ahead and also increase the meshing. Let me go to finer, and now you can see that the mesh has nicely resolved the cylinder, right. So, now this is what looks good to proceed further. So, let me go to my study 1. Let me write electrical study. So, my study 1 is electrical study, where I am only performing the electrical analysis. Let me go to compute and click on compute. So, now you can see the voltage distribution or the potential distribution along the polysilicon. Now, if you want to see the current distribution, the current profile, so there are many ways to see. The first way is to know how the current is flowing through. One of the way to do that would be right click on the results, 3D plot group. In the 3D plot group, I can create an arrow volume. In the arrow volume, I can search for the current. So, in the replace expression, I can search for the current density and click on plot. Still now I am not able to visualize the current properly. Ideally, the voltage which shows that it is very high over here and it is decreasing like this, right. So, our current profile should also be similar to the gradient of your potential. The better way to recognize it would be to change the grid points. So, let me just go ahead and change the grid points. Hopefully, we will be able to see those. So, in x and y, I need to increase the grid points, and in the z point, let me use only 1. And now you indeed are able to see the current flow. So, now you can see that the potential which was applied very high over here is actually making sense, because the current is actually flowing like this, and it is going to turn over here, and then it is going to move back towards the minus x direction to the ground where you have given. So, this actually makes sense, the results make sense. So, it is always good that once you actually get the results, you also validate the current profile, how much voltage are you getting, to revalidate the whatever input that you are giving is actually being conceived by your system. Okay, so the next thing is to understand there is a current flow, and we need to understand where the current flow is going to be very high. To understand that, what I will do, I will create one 3D plot group, and I can create one multi-slice plot. Multi-slice plot would be somewhere in the more plots over here, and I can search for norm of current density. So I can just search about current density, and over here, and now you can see that the current density is very high somewhere over here, that is in the thin leg over here and over here. This means that the current at this particular the current density at these particular legs are very high as compared to the other domains. So that also means that the losses which is proportional to the current are also going to be higher at these particular legs. So let us also see now if there are losses because of the Joule losses, how I can evaluate this. One way to see it would be again the multi-slice plot. So I can create a 3D plot group by right clicking on the results, and I can create one more multi-slice plot, and I search for losses. I have volumetric loss density and volume that is complete electromagnetic, and then only the electric part. There is no magnetic component, so we can choose any one of them. Let me choose QH and click on plot, and indeed that's what it is showing me. The losses are very high at the both of the legs. You can see over here thin legs. It is even high at the corners, and that's the same thing what the current density was showing, that wherever the current density is high, the same place the losses are going to be very high. So these losses are, as you can see, in order of watt per meter cube. Now you still have the losses, but you don't know the losses are going to lead to what change in the temperature. This system is working with which ambient temperature, you don't know that, right, because we have not assigned it yet. So let us also set up a thermal condition to see how the temperature rises if we give a voltage of 5 volts in room temperature. Before to that, what I will do to so because we have many studies that we are going to have, to reduce the complexity, I will group my results. So I select all of them, and then I right click on the results on the selected nodes, and I click on group. So my group 1 is electrical analysis. The next part is I am going to add the thermal physics. So I go to physics, add physics, and I add now in heat transfer in solids. Now you can see that once I again go back to my polysilicon, earlier only the electric conductivity and the permittivity were having a green tick mark, but right now as we have added the thermal physics, the heat capacity at constant pressure, the density as well as the thermal conductivity has been activated. Again you can see that the thermal conductivity is a function of temperature. The capital T now is actually coming from here once we do the coupling. Even the conductivity, the electric conductivity as a function of T, the capital T would be coming from the heat transfer in solids. In this, let me just go over here the thermal conditions, and as you can see over here, we would be giving fixed temperature to the places where we have attached it to some other boundaries. For example, the dimples over here, this one and this one, which are on the cold arm, and the anchors which are this one and this one, and all the others we are going to give a convective heat flux with a heat transfer coefficient of value 5. So let me go to physics, and now over here let me add the fixed temperature. To add the fixed temperature, I right click on heat transfer in solid, I go to temperature, and over here I click on these boundaries, and by default this is the room temperature, right. So as well as the top of the dimple, I click those. So these boundaries are going to be attached, or it is going to be tied up with a particular temperature, and it cannot increase from that. Now we are also going to add the convective heat flux. To do that, just right click on the heat transfer in solids, and you can use the heat flux boundary condition. So I choose those, and I just click on my graphics, left click, and then I use Control A. That selects all the boundaries, and now I need to deselect the boundaries of the anchors and the dimples. The next thing, are we giving an inward heat flux? No. Are we giving convective heat flux? Yes. So I enable this, and I also need to give an external temperature which is a room temperature by default. That looks fine, and the heat transfer coefficient as 5, which means that there is a airflow, not even airflow actually, there is air surrounding this particular system. If there is airflow, the thermal expansion the heat transfer coefficient would increase. If there is water which is cooling the system, it will even increase even faster. So this kind of heat transfer coefficient actually depends upon what is the ambient temperature, what is the cooling condition that you are trying to give. For example, you can also give over here external natural convection, internal natural convection, external forced convection, and internal forced convection. These are all the options that are available. So we are done with the physics, with the thermal physics. If you want to go back to solid 1, you can see the actual equations that is actually being solved over here. Similarly, in the current conservation node over here, you can see the actual equations that is being solved by electrical physics. Now coming to the coupling part, how the electrical physics and the heat transfer physics are getting coupled. That if you would have been careful enough, you would have seen that this multiphysics node was not coming up before, but right now it has come up because there were two physics that would be coupled. There are many automatic coupling. In addition to that, there are also manual coupling. So if you want to add the automatic coupling, just right click on the multiphysics node, and you can see over here the electromagnetic heating. So let's click on the electromagnetic heating. This, as you can see, it couples your domains and the boundaries from the electrical currents to your heat transfer in solid interface. So whatever losses that were getting accumulated by your current that is going to flow, all the Joule losses are going to get transferred into the heat transfer in solid part, and that would be responsible to the rise in the temperature. So now let me go to the mesh. Okay, I need to add one more multiphysics coupling, that is temperature coupling. And let me go to the mesh. There is no change in the mesh anyways, so we can now go ahead and add one more study. So I go add one more study, and over here I add one more stationary study. Over here I write electrical and thermal analysis, because we are going to do both now, and you can see that both have been activated over here with the multiphysics node. It is very important to note that your results would be accurate enough only if you match your material properties as much to your real properties. If it deviates from your actual experimented material property, then the results also will also deviate. So it's very important to come back and see to the materials that you are using, because this is very important. Okay, so let me go to my study 2 and click on compute. You can also see the convergence plot with the error. You can also manually tweak the amount of error that you want to use, that is a related tolerance error that you want to use to make the system converge. So now you can see the first plot is electric potential, the second plot is the temperature, and as we know, as we also have seen before, that the temperature rise would be somewhere over here, right? Because if you see the electrical analysis in the in the losses plot, the power losses plot, this is the power loss plot that you can see over here. There are a lot of heat losses over here. So this is the temperature plot. Now for example, you want to see the maximum and minimum values over here, you can see over here. If you want to see the actual values without the exponential part, you can actually come to the number format and you can use the precision values, you can increase that. So like you can see that it's very high temperature. And it's also important to note that COMSOL is a tool which will help you to give the results, but it will not help you to tell that if it is going to melt or not. This is the part that we have to do by ourselves. For example, if the melting point of our system is around 2000 Kelvin, right? So COMSOL will not tell you that it has like the temperature has rose beyond 2000 and it will give an error. So it will not give an error, it will tell you that it is still increasing the temperature, but you have to yourself understand that it's gone more than the melting point, and this is how it actually stops. Now for example, you know the temperature and you want to now see the temperature plot from this point to this point in a line segment. How is the spatial distribution? To do that, I can create a 1D plot group. So I right click on the results, I create 1D plot group, and over here I right click on the 1D plot group and create a line graph. In this line graph I select which line I want to use. So let me use this line, and I want to evaluate my temperature. One way is to directly enter the expression over here. One alternate way is to just click on replace expression and search for temperature. Before to it, we have to be sure that we are using the dataset of study 2. So let me go ahead and choose my dataset at study 2, that is electrical and thermal analysis, and then search for the temperature. So you can see that temperature profile variable has arrived over here. So I double click on that, and whether I want it in Kelvin or I want it in degree Celsius, I can use that and click on plot. So now you can see the spatial variation of temperature along this particular line. Okay. The next thing is to perform the structural analysis. Before doing the structural analysis, what I will do is again group my electrical and thermal analysis together, and I can write over here electrical and thermal analysis. The next part is to perform electrical, thermal and structural analysis. So let me go to my presentation and see how are the structural conditions. You can see over here there are fixed boundary conditions over here, here and here that are on the anchors, and on the dimples we have roller boundary condition over here, here and here. That means that these boundaries can actually roll. You can give a particular translation motion, but you cannot give an up and down motion to the roller. However, the fixed constants are not allowed to move in any direction. So let us go and to the COMSOL and add this physics. So we have already added the electrical physics and the heat transfer physics. The next thing, I go to the physics, add physics, and I add the heat transfer in the solid. I just double click on this, and over here, oh sorry, I added the wrong physics. I need to add the structural mechanics. So I go to the physics, I go to the add physics, and I go to the structural mechanics and I add solid mechanics physics. Again we can go to the material section, and you can see now the Young's modulus has been enabled over here, the Poisson's ratio has been enabled over here. Both are a scalar value. If you want, you can also make it as a function of temperature, conductivity by just writing over here. You can make it a temperature dependent material property by just writing over here as, for example, 300 divided by T, for example. Okay, so this is just for example. Let us go with a constant value. In my solid mechanics, as you have seen over here, we are going to give roller boundary condition at the dimples and fixed boundary condition at the anchors. So let me right click on solid mechanics and I give a roller boundary condition. You can see the equation. So all the boundary conditions, the domain conditions would be giving the equations. So from the equation also you can understand how the motion is going to be. It means the normal motion of your boundary is 0, while it will allow the tangential motion. Now we go ahead with the fixed constant. Again right click on the solid mechanics, add the fixed constant part and choose this boundary. You can see the equation that u is equal to 0. So both tangential, normal or any angular displacement are not allowed. The next thing is again to use the coupling. So we have already established the coupling from electric currents to the heat transfer, that is the Joule losses leading to the rise in temperature. Now we need to couple the rise in temperature to the structural mechanics using the thermal expansion. So because of the rise in temperature, what is the thermal expansion? The way to add that would be right click on the multiphysics and then you click on the thermal expansion. The other multiphysics node would not be of interest to you as of now. And then I add my domain. Once I add this, you will see that okay, thermal expansion coefficient is been added. That is also a function of T. So you can go within it. You can see alpha over here, how it is a function of T. So we have added the thermal expansion. So we go to the study node and add one more study, a stationary study. In my stationary study 3, I write electrical, thermal and structural analysis. And over here you can see that I have enabled all the 3 physics along with the 3 multiphysics node. Okay. You can see over here the rest of the boundaries are free. By default all the boundaries are free, but if you run your system stationary analysis, that is steady state analysis, with the free boundary condition, your problem becomes ill posed and you will get some non convergence issue. So it's always good to assign some fixed constraints boundary conditions. So let me go to my study 3 and click on compute. In the progress bar you can see the what solvers it is using, how much is the iteration. So we are not going to cover in detail the solver configurations. You can see the convergence plot over here. If you have any questions, please do not hesitate to ask your questions in the form of chat or the means that is allowed. Yeah, so you can see the results now. You have already have seen the temperature variation, isothermal contours and the stress plot. So now you can see that the stress which are being developed with the surface plot, and if you want to see it in Newton per mm square, you can just click on over here and search for Newton per mm square or MPa, or you can just directly mention over here Newton per mm square. Click on plot. So we will see the stresses over here. You can enable the maximum and minimum values so to see what are those values. If you want to see the displacement, so in that case you can just right click on the results, 3D plot group. In this I create the volume, and in this I search for displacement. So you can see over here, okay, again we have to see the data set with which we are studying. So we are doing electrical, thermal, structural analysis. So let me choose this, and over here I search for displacement. So you can see this variable solid.disp, that is total displacement. So let me choose this, and you can see that it shows around maximum. So maximum I can enable over here a maximum displacement of around 21.2 micrometers somewhere over here. Okay. Now if you want to see or visualize how much deformation is going to occur based upon the voltage that I have given, I can use I want to visualize how much displacement. So I can just right click on the volume 1 and click on deformation. I can enable the scale factor as 1. So this is how much it's going to displace. So this length of this one, if you want to see, you can actually evaluate, you can measure actually by right clicking on the geometry, go to the measure using the geometric entity level as point, and the length I can measure from one end to the other end. So it's around 26 micrometer. The length are not that big. Length, okay, sorry, let me start from this point and this point. Yeah, so length, total distance, the total length is around 200 micrometers, and that particular device is bending around 21 micrometers along the minus y direction. Okay, so that's good enough. Now, however, I want to know that if I change my potential, how much is my displacement going to vary. In addition to it, I also want to see the maximum temperature that is uh, occurring within my system as I change my voltage, because I know that my polysilicon would also be having some kind of a melting point. So, let me just go to internet and search for melting point of polysilicon. So, it is around 1400 degrees Celsius. So, now I know I have some kind of threshold value with which it should not go increase, the maximum temperature should not increase that. So, now what I can do is I can sweep my voltage. To do that, I can just right click on the study 3 and I can do a parametric sweep, and over here I can add my voltage V naught, and over here I can write the range. I can just click on the range. I can start with 1 volt with a step of 1 volt and a stop of 5 volts. So, it is going to move from 1 volt to 5 volts, and then I click on compute. So, till the time it computes, there were a couple of blocks on fluid structure interaction that I will like to showcase you. This is one of the block, and so all the blocks are having very nice animations. So, it would be like very nice to actually understand the physical intuition of the physics. For example, this is a water balloon during inflation. What are the velocity, magnitude, stresses that are being developed, and all those things are available. So, this is the fluid structure interaction problem where the balloon is getting filled. Fluid structure interaction, we had one more block. This is for heart valve. So, you can understand with these change in the flow of velocities, how the valve is actually moving. So, it requires moving mesh technique over here. So, such kind of fluid structure interaction modeling could also be performed. So, over here you can see this what kind of solvers are we using. So, we are using segregated solver. There are fully coupled solver, segregated solver. These are the two basic kind of solvers. Fully coupled solver takes all the physics together. Segregated solver takes it step by step. There are also two types of solvers, that is stationary it's direct and indirect. Direct is more robust, it takes lesser time, but it takes a lot of memory. The iterative solver actually takes longer time, but it actually takes less memory. So, we have received we have got some results. So, we have now, you can see that we have 5 potentials. So, in the 3D plot group I can see for 1 volt we are getting okay, I need to go inside this. Yeah, for 1 volt we are getting the displacement of 0.02. For 2 volts we are getting 1 micrometers, 3 micrometers, 8.23 and 2.15, like this. So, now if you want to see, if you want to create a graph of if you change the voltage, how much is the change in the displacement, I can just right click on the results I can create a 1D plot group over here. I can create a point graph, and I can choose this point, okay, and I can ask it to plot for, once I select the data set, appropriate data set, that is study 3, I can ask him to plot the displacement. So, I search for displacement, somewhere over here, and I double click on this, and I just click on plot. So, it would be automatic, the x axis would be parameter in voltage and y axis is going to be my displacement. So, you can see that as the voltage increasing, the displacement is also increasing, and it's not it's a non-linear curve that we want to see, that you have already seen. You can also enable the markers over here. So, you can use asterisk marks with in data points, that is at whatever points you have swept you will get the results. Okay. Now, the next point is to see also the temperature. Okay. So, the temperature is the maximum temperature. To do that, what I can do is I can just right click on my definitions, I can create a component coupling, and over here I can choose maximum. So, I choose the maximum over here, select the domain over here, and to make this max op1, that is the operator name max op1 available in the post processing, I need to right click on my study 3 and click on update solution. That is it, and over here I need to create a 1D plot group again. So, I right click on the results, I create 1D plot group. In this 1D plot group, I go ahead, right click on it and create a global plot. Here I will use the same operator max op1 as a function of temperature, and I use the data set as my third data set and choosing all of them. So, I will use all. My x axis again temperature, sorry, voltage, and now you can see the temperature, max temperature is increasing again as the voltage is increasing, and I can add an asterisk marks with in data points. So, if you assume that our melting point is around 1500 degree Celsius, so let us make it degree Celsius. So, if it is around 1500, then your device would only work till 4 volts. If you go more than 4 volts, then your device is going to melt, for example. Okay. So, this is how you can actually do the analysis. One more thing that I wanted to show is if you want, so right now if you want to share this, so let me just group this first. Now, this is the electrical, thermal and structural analysis. Now, if you want to share this particular model, for example, you could be a researcher, or you could be a student, or you could be a professor who are taking this course, and you want to share this complete analysis with your colleague. So, if you are a professor, you would like to give it as an assignment for your students, and they want to change some kind of a parameter and run and get the different kinds of results at different operating range. Or you could be an R&D person, and you are specialize in electrical, thermal and structural analysis, but you want to give it this kind of model to your design engineers who would be designing the system. So, they actually don't need to actually go through the complete model, they are only interested in the results. So, they can actually vary the input parameters and finally get the results. They are not interested to see what is happening over here inside. Or you could be a student who have make this model and is going to give a thesis presentation to a professor, and they are also the professors who are attending your thesis presentation, they are interested to actually see in different operating voltages or operating conditions, what are the different conditions, right, at that time impromptu they want to change it. So, one way is to create an app. So, in the next couple of minutes I will just show you to conclude the session how to create an app. It's very simple to create an app. That's how we will just show it. To do the app, it's important to actually parameterize. So I can again go to my range. So I will write start underscore v, step underscore v, and stop underscore v. So these three parameters I have defined. That is my start voltage, my step voltage, and my stop voltage. I will click on replace. Again, it's saying unknown model parameter because I have not defined. So let me write over here as start underscore v as 1 volt. It's always good to write your whatever parameter along with the unit, so that there are no inconclusive results. Step voltage is 1 volt, and then the stop voltage is 5 volt. So it start with 1, have a step of 1 and stop of till 5 volts. Again, it's always good to see that you have not there's no mistake in spelling mistakes and all those things, right. So I have defined the parameters. I know what plots I want to see. So for example, I want to see my thermal plot over here. I want to see 1D plot group 14 and 15. Okay, so I go to my application builder. So only by one click I can go to my application builder, and over here I can just click on new form. Once I click on new form, it's asking me all the parameters that I want to change. For example, if you want to change the geometry, all those parameters can also be given. As of now, we will give the start voltage, step voltage, and the stop voltage. The actuator length could also be given, for example. So, if you want to vary the length and see how the temperature is varying, that also is possible. Then the next thing is the graphics. What do you want them to see? For example, you want them to see the temperature. You also want to see the stresses or the displacement. You also want them to see the how the rise in temperature occurs with the voltage, and the displacement with the voltage. On the right side, you will see the graph or the form that is being built, and then what buttons or what kind of analysis that they want to perform. They want to do only electrical analysis, electrical and thermal, or electrical, thermal and structural. So as of now, let me give electrical, thermal and structural analysis and click on add selected. And if you want, you can also add all the study, the first and the second one. So and just click on OK. So this my first results over here. I can just move and modify all of them. Make it little bit large, so easy to visualize. Okay. So now the compute button somewhere was over here. So here I can just write over here, and I can change the text as electro thermal or thermo structural study. Okay, so I can keep it somewhere over here. I can move my actuator length somewhere over here. So this is my voltage conditions, this is my geometry conditions, and then this is my compute button. So which kind of analysis I want to do. So I click on test application. So this is how your app would look like. So they can your professor, your student or your design engineers can actually go ahead and change the actuator length, for example 300 micrometer, and then just click on this compute, and where the next set of results would be coming up. Okay, they can also change this start voltage, for example 5, and step of 1 to stop of 10, and then they can compute the study and see the change in the results. You can also add the parameters as material property and also change the material property over here. So this particular could be actually shared with your students, and they can actually, this could be a standalone kind of a thing, and they can actually vary all these parameters and gain a lot of understanding of the system by themselves. Okay, so this is how the complete simulation of COMSOL is. I hope you enjoyed the session. Thank you for attending the session. If you have any questions, please do not hesitate to ask us. We will try to respond it as soon as possible. Thank you. Have a good time.